This is lecture 15, where we will be looking at how we can actually solve higher order ODEs. So if you look at the previous lectures that we have covered on the solutions of ordinary differential equation, all the ODEs that we have covered so far are what we call first order ODE. So first order ODE in essence is basically an ODE where the order of derivative or the highest order of derivative is 1. So in this case, you have dy dt is equals to a right hand side function. Now what happens if you have higher order ODEs? So what happens if you have functions like this, where instead of dy dt you have a second order derivative of y with respect to t? In this case we have a second order. So if you generalize to your nth order, then dn y dtn is essentially a right hand side function that can be a function of t and y, as well as the lower order derivatives of dn y dtn. So if you are going to use the Euler method, the Hume's, the midpoint on and even the RK4 methods that we have covered in the previous lectures, to solve these higher order ODEs, what you would need to do is you would need to reduce these higher order ODEs into a system of first order ODE. So how do we do that? I'm going to use this simple example. So let's say you have this second order ODE, where on the left hand side you have d squared theta dt squared, and on the right hand side you have minus gl sine theta. So in this case, t represents time, theta is your unknown variable that you're interested in. So in this case, theta is an angle. And okay, so let me write here. So this is your unknown variable, and g and l are basically constants. So like I said in the previous slide, in order for you to solve this second order or even higher order ODEs, you need to reduce it into a system of first order ODE. So how do we do that? We do that by introducing a new variable. In this case, we say that d theta dt, which is the first order derivative of our unknown variable, is equivalent to omega. So the new variable that we introduce here is omega. If d theta dt is omega, then d squared theta dt square is simply d omega dt. So from here, what we can write is that since d squared theta dt square is d omega dt, this will also be equivalent to minus g over l sine theta. So this is our first equation, and this equation right now contains two unknowns, your theta and omega. So you need another ODE to complete this system. So that second ODE comes from this new variable that you have introduced. So here you have d theta dt is equals to omega. So you have equation 2, and these two equations would be your system of first order ODE. So from here, what you can see is that from your original ODE, which is a second order ODE, you have reduced it into two first order ODE. So if you look at equation 1, the highest order derivative is of order 1. The same goes for your equation 2. Okay, and it involves two unknowns given by theta and omega. So this is how you will reduce a system of higher order ODEs into, this is how you reduce a higher order ODE into a system of first order ODE. Now the key thing to remember here is that the number of ODEs that you get, so when I say number of ODEs, I mean the number of equations that you get defining the first order ODE, depends on the order of ODE of your original equation. So in this case, if your order of ODE is 2 or second order, you should end up having two first order equation. In other words, if you have third order, when you reduce it into a system of first order ODE, you should get 3 first order ODE. So let's demonstrate that by looking at this ODE here. So the highest order derivative is 3, which tells us that this ODE is third order. So how do we reduce it into a system of first order ODE? We need to introduce new variables, and because we have third order, we would need 3 dependent variables. So the first one, we can set dy1 dt to be equals to y2. Alright, and the second one, if we look at this equation here, dy2 dt is essentially d squared y1 dt squared. Okay, and finally we are going to introduce a third variable, where we write dy2 dt is essentially the same as y3. Now, if you have dy1 dt to be given by y2, and if you have the second order derivative of y1 to be given by the first order derivative of y2, and finally if dy2 dt is equals to y3, this entire equation we can reduce it into a system of first order ODE. So how do we do that? So you can see for this particular, okay, let me call these equations A, B, and C to make it easier. So let's say this is equation A, this is equation B, and this is equation C. So from equation C, if I differentiate equation C with respect to D, I get dy3 dt. On the left hand side here, you end up with d squared y2 dt squared. And what is y2? Y2 from equation A is equals to dy1 dt. So this is also the same as the third order derivative of y1 with respect to t. So if this right now is equals to dy3 dt, then our original equation, we can write the first term here as dy3 dt. Okay, so we're going to move everything here to the right hand side. So this is equals to minus y2, and you have d squared y1 dt squared. So what is d squared y1 dt squared? d squared 1 dt squared is equals to dy2 dt. But what is dy2 dt? dy2 dt from equation C is equals to y3. So I can simply write this as y3. So this is my first order equation. Okay, so remember what I said earlier, if you have a third order ODE, you should have 3 first order ODEs after you have reduced them. So we already have our first equation. The second equation is simply equation C, so I can also write dy2 dt to be given by y3. This should be my second equation. And finally, the third equation would just be equation A, which I can write it as dy1 dt is equals to y2. So here you have a system of first order ODE that contains 3 equations, and all of them are first order. So the key thing to remember when you're reducing your higher order ODEs into a system of first order ODE is to see whether what order of ODE that you have. If you have a 5th order ODE, you should have a total of 5 first order equations. Alright, and when you reduce it to your first order equation like this, try to make a habit of writing all the first order derivatives on the left hand side and move everything to the right hand side. This will help you because if you look at your right hand side and your right hand side contains any derivative, it means that you have reduced your ODE incorrectly. So for example, this equation 1 here, if I'm going to look back at the original equation, you can see that dy3 dt, this third order is replaced by this term. And then on the right hand side, we have y2 times the second order derivative of y1. So if you look at the second order derivative, i.e. your equation D, you will have dy2 dt. Now you have first order derivatives appearing in both left hand side and right hand side, which means equation 1 is not really correct. So what you need to do is you need to reduce this further by using equation C to write it as y3. Alright, so I'm going to stop this part here and I'm going to pick it up in the next part of the lecture. Okay, so now that we have reduced a higher order ODE into a system of first order ODE, how do we actually solve this system of equations using one of the techniques that we have learned so far, i.e. your Euler, your Hilms, your midpoint, or your RK4 method. So in MATLAB, it is easy for us to handle a series of unknowns because we can write it as a vector. So if you look at the example that we have considered before, so if we have this third order ODE, using the steps that I've just outlined in the previous part of this lecture, we are able to reduce it into a system of 3 first order ODEs like this. So in MATLAB, it is easy for us to actually write this as a vector form. So this particular set of equations here, I can basically write it as, on the left hand side, we have first order derivatives. So in vector form, I can write it as my y prime t, and on the right hand side, I have my right hand side functions. So you have f, t, and then you have your vector y as well. Okay, so the curly brackets here represents your storage in MATLAB in vector form. So in other words, in your left hand side here, essentially what you get is you get y prime 1 t, your y2 prime t, and y3 prime t. Okay, so this vector form tells you that there are actually 3 inputs or 3 elements to your vector here. So the 3 inputs are your dy1 dt corresponding to this, dy2 dt corresponding to this, and dy3 dt corresponding to the last one. And of course, on the right hand side, you also have your right hand side functions for each of your derivative. So on the right hand side, you would have y2, which correspond to the first ODE. You would have y3 corresponding to the second right hand side of your ODE, and then you have minus y2, y3. Alright, so what is y? Y in vector form is essentially the storage of your unknowns y1, y2, and y3. So let's say we want to use Euler method to solve this. We know that Euler method, in one-dimensional form, you have yi plus 1 is equals to yi plus h times the right-hand side evaluated at I. But if your unknown right now is in vector form, then you can actually rewrite your Euler method in vector form. All this can be easily done with MATLAB. So on the left-hand side, you have in vector form, such that on this left-hand side, if you expand into the 3 unknowns, you have y1, y2, y3 evaluated at point ti plus 1. And then from your y at ti, again, if you write it in full, you will have 3 rows here given by y1, y2, y3 at ti. And finally, h will remain the same because h is referring to the step size. And your function f here, you will have your function f1, f2, f3, where f1, f2, f3 are the right hand sides of your equations. So this here is your f1, this is your f2, and this is your f3. Now this thing then can be implemented using the Euler method that you have learned from your previous lecture. So there wouldn't be a significant changes to the MATLAB code that you have developed before this. The only change that you need to do is to write your unknowns in and write your known values or your functions in terms of a vector. So although this example is shown for a system of 3 ODEs, you can actually extend it to any number of ODEs that you have. So if you have in general an nth order ODE like this, when you reduce it to a system of n first order equations, then this can be extended, or this approach, which is done with the Euler method, can be extended to any number of ODEs that you have. That is one thing. The other thing to note is that you can also apply this method here using the Hume's, the midpoint, or the Runge-Kutta method. Okay, so of course on the right hand side wouldn't be as simple as this anymore. If you use midpoint method, then you would have the 3 corresponding functions here for the midpoint method. If you use the RK4, where over here you have h/6 of k1 plus 2, k2, 2k3 plus k4, then on the right hand side it will be given by, again, a vector of your right hand side corresponding to what you have here.